In Calculus 1, you learned how to find slopes of implicitly defined curves, such as when you set this equal to a constant. Oh, and let's take this to be, for example, 1. When you had in Calc 1, you had situations where you had curves defined implicitly like this. And you were wondering about slopes along those curves. And you used implicit differentiation. If I set this function equal to 1 and use contour plot, I get a single curve. There it is. Kind of a weird shape. In fact, it's got 2 pieces to it. I might wonder at a certain point xy in this curve, what's the slope there? In Calc 1, you used implicit differentiation. Assume y is a function of x. And differentiate with respect to x based on that assumption. The derivative of x squared is 2x. And differentiating with respect to x. The derivative of y cubed with respect to x is not 0. Because when I'm using implicit differentiation, I'm assuming y depends on x. It's a function of x. It's also not 3y squared, but it's instead 3y squared times dy dx because of the chain rule. That's the chain rule right there from Calc 1. When you differentiate minus 3y with respect to x, assuming y depends on x, you get minus 3 times dy dx. 1 is a constant, it differentiates to 0. And then you solve this equation for dy dx. And what you got, some multiplication there, is dy dx in this example is negative 2x over 3y squared minus 3. And then if you wanted to slope at a particular point, you plugged in the coordinates, x and y. We can derive the exact same formula in a new way here. dy dx turns out can be thought of as the opposite of the partial of f with respect to x divided by the partial of f with respect to y. That's a general formula that works as long as you're not dividing by 0. Where does it come from? It comes from applying the chain rule. You look at this equation, z equals f of xy, and you try to find the partial of z with respect to x, assuming y depends on x, using the multivariable chain rule. Same assumption you do with implicit differentiation. And what you get is dz dx times dx dx plus dz dy times dy dx. Huh? Dx dx? Is that really right? Yes, and it equals what you would guess, 1. And maybe we should have written a regular dy dx here. And when z is equal to a constant, when you differentiate the right-hand side of this, you get 0. The constant doesn't depend on x. And what you end up doing is solving this equation for dy dx, subtract dz dx from both sides, then divide both sides by dz dy, and what you'll do is you'll get this equation with f's in place of z. But z is a function f of xy, so that's not a big deal. Very quick, maybe not super precise derivation of this formula, but that's another formula you're going to see in the reading and should be able to use. Is it beneficial to use this? Yeah, sometimes. Sometimes implicit differentiation can get really, really complicated, but doing this is a bit simpler. So this is something worth knowing.